아직 한참 시간이 남았지만 한번 출석을 부르고 안 오신 분들 확인하도록 할게요. 이재혁 씨, 네. 오하늘 씨,
네.
신준호 씨, 이승빈 씨, 이정태 씨, 이충하 씨, 정상아 씨, 네. 홍주표 씨, 네. 김민선 씨, 네. 그리고 김유신 씨, 배민경 씨, 배서령 씨, 서현 씨, 조대현 씨, 최승규 씨, 김성주 씨. 자, 그래요. 자, 여러분들 어떻게 그 녹화된 동영상을 좀 보고 계신가요? 보고 계세요? 녹화가, 그러니까 제가 제일 걱정되는 것 중에 하나가 여기서 제가 제 방에서 할 때는 딱 그 이어폰을 쓰고 마이크를 바로 앞에다 두고 말을 해가지고 녹음이 잘 됐을 거라 생각을 하는데, 여기서 오프라인 강의를 하면서는 얘는 지금 적절한 거리를 잘 확보를 못하는 것 같아요. 그러니까 좀 거리가 먼 것 같아요. 그러니까 혹시 소리가 좀 작나요? 들어보신 분 있으면.
멀어지면 조금 작게.
아, 그래요? 그러니까 제가 뭐 예를 들어서 흥분을 해가지고 이쪽으로 간다든지 이러면 소리가 작아지고. 그렇군요. 네. 되도록이면 그러면 여기 붙어 있는 게 제일 좋겠네요. 붙어 있어 볼게요. 이게 또 그게 제 맘대로 잘 안 되는 편이라. 수업이 어렵지는 않아요. 수업에서 주로 제 그 강의가 한 학기가 끝나고 나면 그 평을 들어보면 어떤 사람들은 뭐 어렵다고 하는 사람도 있었고, 반면 너무 쉬워서 재미가 없었다고 하는 사람도 있었고, 그래서 스펙트럼이 다양해서 대체적으로 그냥 쉽게 가자라는 식으로 강의를 하고 있습니다. 하지만 제가 쉽게 강의를 한다고 해가지고 이 과목 자체가 그냥 이 정도만 알아서 되는. Okay, so we are now talking about the lecture level of my lecture. So there are various spectrum, so quite a wide spectrum about students' feedback. So at the end of every semester, we take the feedback from students, the registered students, and that is really widely distributed. And some guys say that, oh, that was too difficult, and some guys say that was too easy, so that was really boring. So yes, so usually I took the last so the first one. So I usually try to explain as simple as possible, so or not to introduce many equations, although there are many important equations in this course, but I try to avoid them as much as possible. But please note that although I'm not talking about equations in this lecture, it does not necessarily mean that you don't have to understand about the equations. Equations are important in this field, and so if you are interested, then please do your self-study, and it is always more than welcome to ask me any question about this lecture course. So I strongly recommend you to do more than the lectures. So if you do some regular review of our lecture, it's good, and you will have anyhow good score from this course. But taking A or A plus in this course does not necessarily means that you are a good student in this field. So you should show your ability if you are really interested. So that is my some recommendation. So sometimes since my lecture is too easy, so they mean that your former my former students think that, oh, it's enough. So just a qualitative description about this topic or lecture content is enough, but that is just the very first step for your study in this field. So later you have to be able to have quantitative analysis too. Okay, so time is quite close to 8 o'clock in the morning. So I want to check once again your attendance. 신준호 씨, 이정태 씨, 홍주표 씨, 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨, 그리고 최승규 씨, 김성주 씨, 미스터 마니케. 누구시죠?
신주.
신준호 씨요?
네.
입니다. So do you have any question before starting our the real lecture? Maybe you have any question? Then yes, please.
저희 배운 그 구조에서 이게 게이트 볼티지가 양수로 있을 때 이제 그 네거티브 차지 덴서티가 이제 존재해서 그 일렉트릭 필드를 이제 상쇄시키는 그런 역할을 하잖아요. 근데 게이트 볼티지가 0일 때도 그 네거티브 덴서티가 존재하는데, 그러면 0일 때는 그 일렉트릭 필드가 안에서 어떻게 존재하는지가 궁금합니다.
Okay, so have you all understood his question? So let me just repeat once again, because here we have other students. So he just summarized our previous lecture. So let's say that this is oxidalism and this is silicon, and the typical case is we apply certain voltage to metal. So that voltage is typically called as gate voltage, because this metal sorry. So I have no idea what is this letter that. Okay, so typically this part here, this is metal, and this is called as gate reason. So that's the reason why this metal voltage is called as gate voltage. And when we have this positive voltage, yes, we have electric field, and that electric field downward was cancelled out or compensated by our negatively charged layer. Okay, negatively charged layer, and you know what it is. The negative charged layer can consider or can contain two different components. One was depleted charge, yes, and another one was the inversion charge. So if we consider depletion charge, that was immobile fixed charge originated from fixed atoms, ionized atoms, and if we consider inversion charge, that is mobile electrons, which shows effectively type conversion from p-type semiconductor to n-type semiconductor. And his question was, okay, that was the situation, typical situation for positive gate bias. However, also we can apply, for example, zero gate voltage to our system. Then what will happen? So the answer is yes. Typically, even in this case, we have the same direction for our electric field. So, however, it is true that compared with V, oh, sorry about that. Something. Okay, so let me just try and make it slower. So, compared with Vg equal to, for example, 0.7 volt, Vg equal to 0.2 volt will have weaker electric field. Let's say that this is corresponding to 0.7 volt, and if we have lower voltage for gate, the metal, of course, this electric field will small, weak. However, still, the direction is not changed, although the magnitude is reduced. So, still, we have to have a negatively charged layer. And in this case, please note that those two mechanisms are completing to each other. So first, depletion layer comes first, and only after strongly sufficiently strong electric field is applied, then the inversion can occur. So if we have weaker electric field due to reduced gate voltage, then this negatively charged layer is almost solely composed of what? Solely composed of depletion layer. So we will have almost no electron, mobile electron. So your answer is, my answer to your question is quite simple. Yes, even at gate voltage equal to 0, we have negatively charged layer. However, it almost contains only depletion charge and almost no electrons at all. So this condition, when you apply gate voltage to 0, there you have no mobile carrier at all. So that is not that good for your current conduction, but that is the beauty of this MOS system. When you apply 0 voltage, then you can make almost 0 carrier inside your system. When you apply the gate voltage like 0.7 volt or something like called VDD, then you can collect a lot of electron at your side. So think about this case. If your mobile charges, so let me just consider the number of electrons, mobile electrons inside your system. And so this is the gate voltage, and sorry about that. So let me just take again. Okay. So let's say that now you have, for example, you have a certain device or certain system whose number of electrons behave like this. Then do you like it or you don't like it? So when you apply your 0 voltage, then you have considerable number of electrons. So even when you apply 0 voltage, you cannot turn off your device. It always conducts. Of course, when you increase your gate voltage, of course you have strong strong, even stronger electron conduction. Oh, that's good. But point is, in this system, if you have such kind of system, you cannot completely turn off your device. Then let's say that you wanted to apply your device to switch purpose. So you wanted to make an electric switch which react as your input voltage, gate voltage. Then it means that this device lack of off state. There is no off state at all. So that makes a serious problems to such kind of device. Then maybe you will feel that, oh, there is no application for such kind of device. But in reality, there does exist a family of devices which shows such kind of behavior. Where can you find those devices? So, for example, even when you apply gate voltage equal to 0 volt, you have considerable number of electrons which actually is not turned off at all. But that is typical case of something called power electronics. So think about power electronics means that you have applied, for example, 700 volt to your system, and if you have this large voltage applied to your device, then your device should be strong enough and robust enough to sustain that high voltage applied, and also should be able to conduct a lot of current to drive huge machinery connected to that device. So in this case, typically power electronics, it is quite common to have such kind of system. Yes, why do we have such kind of system? It is only because in many cases this power electronics is not made of silicon. So silicon is not the best material for power electronics. So usually we introduce other compound semiconductor to build power electronics. Then unfortunately this condition, so usually say we call it as what? Normally on condition. So means that normally when you apply 0 voltage, we do not have the off of our transistor or device. Then of course, although there exists a kind of family of devices, but this is not none of our interest in this course. In this course, instead of power electronics, we are now talking about more related to the analog devices, analog system, analog circuit, or digital system. They are related with the signal processing, so their operation voltage is much lower than that of power electronics. Power electronics, you apply several kilovolts or 100 volts to your device. However, in the case of logic or other devices, then the maximum voltage you can apply is just around point some volt or 1 point something, even 3 point something. So that is much lower voltage. So in the case of this case, typical case we consider in this course, we prefer to have this behavior instead of this black curve. Now we wanted to have this red curve. If we have a red curve, then what happens? When you apply 0 volt, oh, sorry about that. I have no idea why it is automatically magnified, but yes, in this case, when you apply 0 voltage, then now you can have almost no free carrier for your electron conduction. And when you apply high gate voltage, let's say that this is corresponding to your VDD, then you can find a lot of mobile carriers which can conduct. So this is the thing we wanted to have. Then if we have such kind of system, then by applying VDD to your gate terminal, then you will have a lot of electrons. And when you apply 0, then you will have almost nothing. So it behaves like what? It behaves just like a digital system. When you apply 0 over VDD, depending on the voltage applied to the gate, your MOS system, vertical system, just react like a digital system. Okay, if you give me 0, then I will provide 0 electrons. And if you provide VDD to my gate, then I will provide a lot of electrons which can conduct the current. So that is a kind of digital implementation. So finally, I wanted to answer with final remarks on analog aspect of this curve once again. So when we just concentrate on, for example, this part and that part, if we apply either Vg equal to 0 or Vg equal to VDD, then we can have two clearly distinct states. So yes, good for conduction or quite bad for conduction. However, when we have our concentration on this line, then how about this? In this range, once the device is turned on, then now we have linear dependence of number of electrons as a function of gate voltage. So now you can find that this part is really corresponding to a linear circuit, not globally linear. If that is globally linear, then actually we have to have this kind of behavior. However, around this line, yes, for local point, then we can find anyhow that is act as just like a linear system. Of course, please note that I'm using a quotation mark for representing this linear. In a rigorous sense, of course, it is not a linear system. However, around this local point, we can treat this system as a linear system. So simply, I wanted to say that for such kind of behavior, so that is a typically non-linear, yes. However, by selecting proper operation point, for example, this is good for your digital application, this and that, and this part is good for your analog application. So if you apply certain voltage, gate voltage, just around this part, then you will have some analog device, the behavior which is good for your analog application. And when you apply this and that, then you will find that this is best suitable for your digital operation. Okay, so I think that is not that difficult to you understand this point. And thank you for really nice question. And let me just check your attendance once again because yes, so we start up a little earlier. So 김유진 씨 계신가요? 네. 배서령 씨도 계신가요? 네. 그리고 최순규 씨, 네, 최순규 씨, 김성수 씨. Okay, so thank you for your nice question, and let me just go to our main lecture. Okay. Do you have any question? So, okay, please.
그 지난번 과제
Mm-hmm.
프로그램 4번에 대해서
음.
풀이를
for problem 4, the last one. So you wanted to have some explanation. Okay, sure. So I will love to have it. So let me just visit GitHub. Then EC what 22S. Okay, then we can visit resources. Then let's check that it shows. Okay, so as you can see here, now we have the inversion number of inversion carrier mobile electrons as a function of gate voltage. So this second graph is just representing the same quantity with the first graph. So let me just show you the first graph first. So here you can see that this is a red colored line, and this is corresponding to electrons, number of electrons. And in problem, so I just ask you to mimic its behavior with two piecewise linear systems. For example, you can easily understand this red curve can be approximated as the combination of this horizontal line, and maybe there, for example, somewhere here, we have some border between two different lines. After that, you can think about this kind of behavior, which is corresponding to your own state. Of course, below this voltage, so this device is not good for current conduction. And beyond this voltage, okay, it's good for current conduction. That was the situation. Now I assume that all of you understand this behavior. However, the point of the second graphs in these resources, if you go to the second part, instead of showing it as a linear scale, so starting from 0, 0.5, 10, 15, 20, 25, now we are representing our quantities in a log scale. Then what will happen? This part, which is dominant in this graph, is just compressed into short range, and the part is shown here, which is just attached to the horizontal line, will show its hidden property. So that is shown in the second part. So when you have a look at here, okay, although to us 0.4 and 0.5, previously when we visit our first graphs, 0.4, 0.5, both of them shows the quantity which is almost close to 0. But now, when you have a look at the second graphs, it is obvious that 0.4 and 0.5 shows almost more than one order of magnitude difference in its electron density. Okay, so therefore, in my opinion, when you apply 0.5 volt to your gate, the metal, you will have almost no electron, because this number corresponding to your 0.5 is still much smaller than that value. You can find that, oh, there is no electrons at all, almost nothing. That's true. But when we make a comparison between 0.5 and 0.4, then you feel that, oh, 0.4 is more hardly turned off. So if we go to, for example, 0.7, then what will happen? That was my question. And I ask you to make a approximation like this. Just assume that this red curve just follows such kind of linear behavior inside this semi-logarithmic scale. Then how does it look like? Just assume this way. So you can calculate the tangential line. Yes, calculated from this 0.4. Then just assume this way, and down to somewhere in the bottom of this scale. Then you will find that extremely small value compared with your 10 to the 9, 10 to the 10, something like that. More or less you will have just 10 to the something, which is just 2. So depending on your slope, calculate. If you make a small mistakes here, then maybe you will have a relatively high value, and relatively slightly steeper value, then you will have an even lower value. But anyway, that's not that important. Point is, in this case, this system called MOS just exponentially react to your gate voltage. That is not seen in this first graph. So in the first graph, to you, 0.0, 0.4, they are the same. There is no electrons at all. But now you understand, even in this case, you will find that this and that will have at least several orders of magnitude difference in their electron density. The total number of electron density will change hugely. Okay, so that was my intention to give you this part. Of course, in this, in this introductory course called microelectronics, we usually take the first view. There is no contradiction at all. So since we are more or less working with this part, once the gate voltage is below than threshold voltage, for example, maybe threshold voltage will be around 0.5 or slightly beyond 0.5 volt. If you apply, for example, voltage below that threshold voltage, then you immediately understand there is no available charge at all. This is good for your first calculation, but if you go to more deeper study in this field, you will find that actually the killing part is corresponding to this part. Whether you have a really small electron or relatively high number of electrons, that really determines your technology. However, this is far beyond the scope of our introductory course. So if you are interested, then please attend our second lecture, Semiconductor Materials and Devices. Okay, so is it good for enough for your question? Okay, and any other question? Those two questions were really good, and I'm quite happy to have those questions. Okay, so if you don't have any further question, then let me just move to our main topic. Okay, but this concept of MOS capacitor or MOS structure is so important. So if you don't understand, then please let me know. Then I will try to repeat my explanation again and again, because this is quite important. Okay, then let me just go to this way. Now, basically the vertical structure called MOS. So vertical means that here we have MOS, and we have extremely thin layer of oxide and relatively thick layer of metal and quite thick layer of silicon. So yes, now that is the situation, and simple. Okay, sorry about that. Okay. Okay, so in this case, now we understand this metal is connected to certain external voltage source, and we apply certain voltage called gate voltage, and depending on its magnitude, we will have a quite much different behavior. So let me just write down once again the number of electrons. Yes, so how can we say? inversion charge will be almost close to zero when your gate voltage is lower than threshold voltage. You know it. So, and what happens if you apply the gate voltage then which is larger than threshold voltage? In this case, now by using this additional voltage means that Vg minus Vth. Now you use this additional voltage applied to your gate as just a normal voltage difference across your oxide capacitance. So now you can write down in this way. Yes. So Vg minus Vth can be regarded as the voltage difference actually applied to our thin oxide layer. So if we have to collect the charge, then Q equal to Cv. Following that rule, we will have this form. Yes. So Q inversion can be written as this form. Of course, this is not exact, so I will just use this similarity sign, but anyhow, sometimes we just believe that this is quite close to equality. Okay, then please note that, oh, it looks good, but if we are caring about the polarity, then we have to be a little bit careful. So Q inversion. What is Q inversion? So the charge originated from inversion electrons. So electrons has negative charges in it. So if we write down in this way, usually Cox is always a positive number. And what is this? So since we are assuming that Vg larger than threshold voltage, again this number becomes a positive number. So when you multiply positive numbers, then you will have positive value. It means that your inversion charge, Q inversion, is following this expression. It is set as a positive number. But you know that this is not the case. You have to have a negative charge in it. So it is good to add negative sign here. But you know, sometimes even a textbook, sometimes we just take the absolute value. So don't be fooled by those mistakes or intentional way. So sometimes authors of a textbook or papers are quite much not that rigorous about sign or something. So, but if we are rigorous enough, then we have to add this negative sign because inversion charge is, in our case, that is negatively charged. So we can have this kind of behavior. So I think that is all for our previous lecture. So in order to understand this behavior, we spend almost 1 or 2 lecture hours for our system. So now you fully prepared to think about the application of this concept. Okay, now we have certain electrons which can be collected and distributed, spread out by changing only gate voltage. Just to conveniently change your gate voltage, you can collect and just to remove the electron. So where is it? That is located just beneath of oxide layer. Of course, sorry about this ugly drawing, so I have to be a little bit careful about drawing. Okay. Of course, in the oxide layer there is no electron at all, so the exact position of our inversion electron can be depicted like this, just beneath of this oxide layer. And I wanted to ask you the typical thickness of this layer. How thick is it? And I wanted to once again ask you what was the thickness of your depletion layer. The thickness of your depletion layer typically have a range of several 10 nanometer or depending on situation several 100 nanometer. That is typical dimension of your depletion layer. However, as I drawn here, the thickness of your inversion charge layer is much thinner. It is extremely thin, and when I say extremely thin, it is just orders of typical number, a few nanometer, thinner than 10 nanometer. Certainly thinner than 10 nanometer. So this is just really close to your inversion charge. Okay. Anyway, now just to changing your gate voltage, now you can generate this shallow and extremely high density layer. Then how can you use these collected electrons for your current conduction? That is now our interest. Okay, if I ask in this way, then one simple question or one simple answer by student is, okay, maybe we can use this path for current conduction. But you know that this is completely wrong, because you know this path, this vertical path is completely prohibited. Why? Because in this system we have a perfect insulator called oxide, so current conduction is not allowed to across this vertical direction. Then what is the remaining direction for us to make the current conduction? Obviously, you understand the remaining way to make current conduction is not this vertical direction, but this horizontal direction. So that's the point. Now, the collection or collection of electrons is done by the vertical field. So vertical field shown here that really collect electrons. However, actual motion of electron is occurring between this left part and right part. That's the point. So now we have to understand this situation. In order to set your voltage into certain region, you have to introduce a certain terminals. So how many terminals are required to have such kind of behavior? So please note that first of all we have to consider this metal. This metal should be connected to external voltage source. Otherwise, we cannot set the gate voltage. So this is gate terminal. Yes. And obviously here we have to have another contact which is used for setting the ground. So you know that voltage is always considered as a relative difference. So just to apply certain 0.7 voltage, that does not necessarily mean that this is high enough. For example, let's say you apply VDD 0.7 and 0.7 to gate. Then what is the actual difference across this MOS system? Although gate voltage is VDD, but since the substrate, that part is called as substrate, and substrate is also biased to VDD, the actual difference is completely zero, then this MOS system will not have any meaningful electrons collected in this part. So, unfortunately, or not unfortunately, sometimes it is really good to have this body. So yes, so here we have another contact for providing a ground. So here we have a contact called substrate. Yes. So when you consider just a MOS system, already we have introduced two terminals. However, this is just for vertical structures, and in order to allow current conduction, then we have to introduce two more. Two more means that for starting of your journey from the left side and the goal of your journey. Your means that your electrons journey right side. Of course, left and right, there is no such kind of preference. So, of course, your journey or your electrons journey can start from right one and ends up at left one. But anyhow, let's say that this is working as a starting point of your electron, and this is ending point of your electron's journey. Then, of course, in order to make the journey or movement of your electrons, it is certain that you have to introduce another voltage source connected to left one, and also you have to introduce another voltage source attached to the right one. Okay, so are you with me? All of you are you with me? So now it is quite clear that at least we need 4 different terminals to achieve our goal. What was our goal? Our goal was to make an electronic switch. So actually switch itself is realized by this one already, by having these two terminals, which is called as a gate terminal and substrate terminal, or sometimes called as a body. So they are two widely used names. So or that is called as a body. But anyway, by having only two terminals in a vertical structure, we can realize electronic switch. However, that switching just shows the number of electrons that should be converted in. Number of electrons should be converted into the current. So in order to convert the change of electrons into the current, we have to apply two additional terminals. And this, the starting point one, is typically called as, this is a universal name, you have to remember. The name is source, and the ending point, the terminal, that is called as drain. So source and drain. What is the source? In this case, source means that source of electrons. Electrons are provided in this part. And where can you find the drain? So please visit a toilet, then you can find a certain drains in your toilet. So there is a certain structure which collect water. So you have a faucet, and when you switch on, then you will have water, and that water is anyhow comes into the drain, and that is the end point of your water using your hand washing purpose or face washing purpose. So this is the drain. So typically you can easily understand when they means that your ancestors, our ancestors, our pioneering engineers first introduced their naming. They thought that just like a water. Okay, here we have source of our electrons, and it's like a river, and after that it arrives at drain, and there is a hole for water, and our electrons are just put into there, and it ends up with just normal electrons. So now you understand this structure should have 4 different terminals called gate, substrate, and source, and drain. You know it, and they have already quite much different purposes. So pair of substrate and gate, they are used as a electronic switch. By action of these two pairs, gate and substrate, they just convert the I have to say clearly say this one. So simply speaking, you have input voltage, and this input voltage is applied as gate voltage, and by action of this vertical MOS system, your input voltage is now converted to what? Your inversion charge. And this change of your inversion charge is converted once again the current by action of two pairs like source and drain. Okay, so it means that how can I do this? Let's say that you are now visiting a baseball ground, and there are two pairs of players. One is a hitter, and one is an assistant. Assistant just toss certain baseball, then hitter try to hit it. So just like this pair of gate and substrate just to provide electrons, and the pair of source and drain really attract or accelerate it to have current conduction. Okay, so now you understand in this structure called as what? Called as in this structure called as in this structure called sorry, I don't know, using my pencil. Here, anyhow, we have this kind of system. This system is called as not just MOS, but it has its own name. Now it is called as MOS. Yes, MOS just means this vertical structure, and now we added two additional terminals to make it as a current conduction, and we call it as field effect transistor. So let me just write down field effect transistor. So field effect means that just another name for inversion behavior. So by applying certain surface field, we can collect inversion charge or don't have inversion charges. So that is represented in this specifier field effect. The point is, this one is now becoming a transistor. Transistor means that so what is transistor? We will explain it later. But anyway, this is the introduction of the structure called Mosfet instead of just MOS structure. Usually, when you say MOS, that is just representing the vertical structure, and when you add field effect transistor, that shows the completely structure which can be used for your purpose. Okay, so do you have any questions? So why do we need additional context like source and drain that can be understood quite easily? Okay. Any Any question? So, are you all happy with this explanation? Okay, good. So, but once again, I want to recommend you, please do your study, and once you start your study by yourself, you will find lots of difficulties to understand details. So details is not that easy like my explanation in this lecture. So in this case, I'm just talking like a story. However, inside it, there are many conceptual difficulties, expected conceptual difficulties. Then please ask me your question. Okay, so then now let's go to the IV characteristics of this one. So if you don't have any further question, then let me just go to my next part. Okay. No question. Okay. Then now we have to think about symbol. So what is a symbol? Symbol means that previously when you talk about PN diode, then what was the symbol? The symbol was just like this. Okay. Now we have two terminals called a cathode and anode. So since they have both of them have a different preference for the applied voltage, we have different symbols. Then how about this Mosfet? How can we write down this Mosfet as a circuit symbol? So now you understand we have four different terminals, then our symbol should have four different legs. So now you are like that. I'm not quite sure why it is reacting to my. Okay, so think about this one. Now you have four terminals. So why don't you just do like this? Yes, 1, 2, 3, 4. We have four terminals, so maybe we can write down it this way. But usually this is not the case. This black box like expression does not necessarily mean that this device is Mosfet. So in order to represent the Mosfet more exactly, we love to introduce this kind of one. So let me just write down. So let's change it to yes. Think about the situation. When we visit our drawing here, gate is located in top. So let me just write down in a similar way. Let's assume that this is corresponding to your gate. Let's assume, and this is your source, and this is drain. Then how can you make a symbol? So you know that the most important part in this device is really the oxide region and the silicon region just beneath the oxide region. So in this symbol, people try to introduce such a kind of thing. Yes, they introduce these two parallel lines. So now you understand what is this parallel line representing. So this is corresponding to your oxide layer. Yes. So this oxide layer, on top we have gate. So we just connect it, and it's left side. So let's say that. Let me just make a long symbol. I will try to make a long symbol from now on. Long symbol means that if I draw in this way, is it correct or not? So you know that in a symbol, this upper part is corresponding to the interface between oxide and metal, and this is not electrically connected at all, and this is not the case. Which one is connected to our source and which one is connected to our drain? So the interface between oxide and silicon is connected to our source and drain. So if I have to draw something, then I would like introduce in this way. Are you with me? So means that this lower line that is corresponding to the interface between silicon and oxide, and just nearby we have source and we have drain. So please have a look at just the schematic or conceptual drawing shown here. So now you understand. Of course here we have body, but usually body is not that, sometimes that can be omitted. So let me just write down in this way, in its most simplest form. We just write down in this way. This is a gate and this is a source and this is drain. This is the symbol for your transistor called Mosfet. So yes, this is the one, but you know that although this is the symbol for your diode, what happens if I draw in this way? Are they different? Or any change in its properties? For example, this horizontally laid one is completely different from this vertically laid one. So no, we can easily make this rotation in our schematic diagram. So let me just make a rotated one. So typically we love to draw in this way. And here we have once again gate. Yes, this gate is this gate. And here we have source. Yes, this is source. And finally we have drain. Yes, we have drain. So why do we draw our Mosfet more frequently in this way? There is a certain reason. Certain reason means that when you draw circuit diagram, so you can think about two-dimensional space, and almost implicitly you have such an assumption. If you go to the top of your schematic diagram, then your voltage is more or less increasing. Yes. And if we go down this in this two-dimensional floor, then you will have a lower voltage. So simply means that this diagram shows that your source part is close to lower voltage region, and drain is corresponding to higher voltage. Okay, so since usually source is biased with lower voltage and drain is biased with higher voltage, so typically we draw our Mosfet in this way. But once again, please note that there is no predefined restriction about drawing our Mosfet in that way. Any rotation is allowed. This is just a convenient practice adopted by many guys. Okay, so here we have this one. Okay, do you have any question about this symbol? So up to now we have discussed about the symbol. It can, of course, it has its first terminal called substrate or body, but I will just omit about that because they are usually connected to either source, I mean that body or substrate this terminal is connected to, usually connected to source. Or we have another choice, like connected to ground or VDD. Also in the case of Mosfet, also we will have ground. So that's the reason why I will not talk about this substrate. Of course, substrate also plays an important role when you go deep into the study, but for a while in this introductory course, we'll just consider 3 different terminals. Okay. So any question up to now? So also I wanted to tell you that the lecture contents in today's lecture is a little bit more than previous lectures, and you can find our previous 2019 or 2020 lecture, recorded lecture, and you can find also several lecture materials related with this concept. So if you are interested, please watch the recorded videos. Okay. Okay. Then if you don't have any further question, then let me just move to the IV characteristics of Mosfet. But before doing that, my final comment on this symbol is like this. The thing is source and drain. Here we have a source and drain. They are structurally identical. That is the thing I wanted to point out. So nobody says that this left one is source, and nobody says that this right one is drain. They are structurally the same. Think about this case. If you have PN junction, then I say that, okay, from now on, I will call this p-type region as a cathode. If I say so, then you can immediately make an objection. No, that's not possible. So, p-type region should be regarded as an anode. Yes, you're right. However, in the case of Mosfet, think about this one. Here we have source and drain, but anyhow, I just say that, okay, I will just swap this source terminal and drain terminal, and I will call from now on this part as source and this part as drain. So can you recognize the difference? So since there is no structural difference between source and drain, actually only from the structure you cannot find nothing. Okay, so point is the role of source and drain is solely determined by the bias voltage. So simply say, let me just consider these 2 cases. I just apply 0 volt to this left contact, and I apply also 0.7 volt to this right contact. Then which one is source and which one is drain? Of course, the terminal with lower voltage should be regarded as source, and this guy should be regarded as drain. Left and right, that doesn't make any sense. Just the relative difference between applied bias voltage just takes the name, so source and drain. So I will just repeat again. Instead of that, why don't we consider the opposite case? I just apply 0.0 volt to our right contact, and apply, instead of this guy, I just apply 0.7 volt to the left contact. Then which one is source and which one is drain? In this case, yes, this guy is source and this guy is drain. Okay, so do you have any question? So there is no predefined way to discriminate the source and drain. They are symmetric. And however, designers also try to make designate, okay, this part will be biased with higher voltage, so this part should be regarded as a drain, and this part is regarded as a source. That is purely electrical sense, not structural sense. That was my final comment on structure and symbol. Then I think that we have just 13 minutes left. So let me just introduce just a conceptual description about IV characteristics of a Mosfet. And the detailed analysis will be postponed to our next lecture on this Wednesday. So I strongly recommend you to visit the recorded lectures, and you will find some equations, and please study in advance. Anyhow, I will explain again in Wednesday lecture. Anyway, it is good for you to study in advance. So now think about what will happen to our IV characteristics. IV characteristic means like this. So let me just write down this. Now we have I. However, I is the symbol for current. However, current is a property of a contact. So, in a rigorous sense, we can define 4 different contacts, like source current, then drain current, gate current, also substrate current, or sometimes called as body current, because this terminal, the first terminal, has two almost equally widely used names. So we can define 4 different terminals. So if we wanted to express our 4 terminal currents as a function of 4 terminal voltages, then our goal should be like this. Okay, IS as a function of source voltage, gate voltage, drain voltage, and body voltage. Also, ID in general, we have to have, yes, I will repeat once again, VS, VG, VD, and VV, and even this final one should be regarded as G, VD, and VV. Okay, so this is the general case. Then please think about our simplified case like PN junction or PN diode. Then what was it? Why our task was so simple? If we have anode and cathode, then let me just repeat again. So let me just repeat again. If we have anode and cathode, then we have to define anode current and cathode current. Also, we have to have anode voltage and cathode voltage, and anode voltage and cathode voltage. That is the general situation. However, what do you remember is not like this. What do you remember? Maybe, if you remember still, then it would be like this. Your diode current is given by certain saturation, reverse saturation current, and exponential VT minus 1. That's it. Then what is the relation between this general approach showing anode current and cathode current? If we have to label certain subscript, then how can you label them? The answer would be, this is corresponding to our anode current, and here V should be regarded as the voltage difference between anode and cathode. You know that cathode is regarded as voltage reference, and the difference between anode and cathode terminals should be regarded as actually applied voltage. So let me just continue this philosophy to our Mosfet. Now instead of 2 terminals, now we have 4 terminals. Now our task becomes much complicated, but one thing we have to keep in mind is, anyhow we have to have what? We have to have a certain reference voltage. So every voltage should be written as the difference, not itself. For example, gate voltage, we do not take the gate voltage itself, but the gate voltage reference to certain reference position, reference terminal. That is required. And among them, so what we do usually is take source that is regarded as voltage reference. Okay. If we take this convention, then now we have already have a certain simplification. Let me just repeat. If we have this source voltage as a reference voltage, then instead of this 4 argument, Vs, Vg, Vd, Vb, now we will have just sorry about that. So I think that my pencil is now gone. Okay. And let me just start a new one. So now instead of our certain terminal voltage, now we can have it this way: VGS, VDS, and VDS. So are you with me? So simply means that here VGS is written as a shorthanded form of the difference between VG and VS. And you know this is VD minus VS. Of course, it's VV minus VS. So previously, in the case of a PN diode, we had 2 terminals, and one was taken as the reference. So we had only one meaningful voltage difference. But now, in 4-terminal device called a Mosfet, we have 4 different terminals, and one is selected as reference. Then what happens? For other 3, we have to care about the voltage difference. So now we have 3 different ones. However, we can make even further simplification. So please have a look at this V minus V, body and source, and typically they are connected. So body and source are connected. Of course, I have to say something. Body and source are sometimes connected, or sometimes body is connected not to the source but to the ground. So in that case, actually our discussion is not valid any longer, but for a while, just to consider this situation. Now our source and body are tied together. Then if we accept this one, then what will happen to our body to source voltage? Since they are connected, the voltage difference becomes exactly 0. So under the assumption, now we can say, now we have only two input voltages. It is like gate to source voltage. Source is the reference, and we wanted to take how high the gate voltage compared with the source. And also we are caring about VDS, so voltage difference between drain to source. Okay, so now think about now think about this subscript here. This subscript is reserved for source, gate, drain, and body. Okay, now we have to prepare 4 different functions of 2 different input variables. Oh, that will be also quite much, but we have also introduced simplification. So let me just do it together with you. So, oh, sorry about that. This isn't clearly not B but D. So IB. Clearly, the gate is isolated. You know that gate is not directly connected to our source, drain, and substrate. Do you remember? So if I draw once again, and here we have source and drain, and here we have substrate or body, and they are belonging to a single piece of silicon. However, where is the gate? Gate is on top of it, and this gate is perfectly isolated by our thin oxide layer. So, simply speaking, gate is isolated and no current conduction through this oxide layer is allowed, and simply we can say that that's it. So then, by applying the Kirchhoff's current law, then what will happen? In this case, we will have IS plus ID plus IB to be 0. So sum of all 4 terminal current should vanish. However, since gate current is assumed to be 0, so we will have the sum of 3 terminal current should vanish. Okay. Finally, from our experience, body current is much smaller than absolute value of IS and absolute value of ID. Okay. Simply speaking, of course, I have to say the magnitude of body current, substrate current is much smaller. So if we adopt this kind of relation, then we can find a really good expression like this. Sum of source and drain current should vanish. Then it means that now ID equal to minus IS. That's it. So now our goal now reduced to this one. We are allowed to consider only this extremely simple form. Taking 2 voltages, the gate voltage and drain voltage, reference to the source voltage, and try to calculate your drain current. If you achieve this goal, then you know everything about your Mosfet IV characteristics. For example, if you ask me, how about gate current? Yes, from our assumption, gate current is 0. How about body current? Okay, from our assumption, body current is negligible. How about source current? Okay, just taking negative sign of your drain current, that will be your source current. That is my situation. So in the next lecture, we'll talk about how can we model this simple relation. Okay, the time is up. Oh, it's 16, so it's over. And if you have any question, please let me know. And we will have online office hour from 1 o'clock in the afternoon. So if you are interested, you are welcome to join the session.